in 4.1 and 4.2, so that means that in my eyes that you understand what we went over in 4.1 and 4.2. I'll check right quick and see just to make sure. I always like to check. And of course, I got to log back in. Been here 15 minutes and got to log back in. Math 120. Nope, I don't see any questions. Oh, that's the wrong class. Nope, no new questions. So that means everybody's good with their homework. Now, I did send y'all a project in Teams. Did y'all see the project? Yes or no?
I saw it.
Okay, well, one person saw it. That means everybody can see it. All right, so you need to look over that. I need you to print it out. I am really not into this. This is something that the department has to do because of some administrators in another building. So we're just going to get by with it as well as we can. So right now I need y'all to print that out and I need y'all to read over it. What they're wanting you to do basically, and I'm going to tell you this right now, is go out and get a package of, or 2 or 3 packs of M&Ms, or 2 or 3 packs of Skittles, or 2 or 3 packs of animal crackers, or 2 or 3 packs of something with either different colors or different shapes. And they're going to want you to do what we did. You know, our statistics that we did, basically they're going to do it with that. And I don't know what, we're going to talk about it after I do some more research on it. I've got to look at the PowerPoint and see what they're wanting y'all to do, but I need y'all to read it and I need y'all to print it out, read it, and go ahead and prepare for it. You can go ahead and be getting your data. Go out and get a pack of M&Ms and a pack of Skittles and count the different colors, count the different, you know, how many breads, how many grains. Or if you want to use animal crackers, go out and get some animal crackers, or the colored goldfish, or, you know, different things that have different shapes and different colors. And they said several, which means 2 to 3 packs. And you can go ahead and you can write down the information. And that doesn't take any you know, any rocket science, just counting colors and shapes. All right, so today we're going to go into probability. There is a picture of Wild Hog Road. And if you know anything about Wild Hog Road attaches West Anderson to Pendleton and Sandy Springs. Now, a lot of you are saying, well, what the heck does Wild Hog Road have to do with probability? Well, I used to travel Wild Hog Road a good bit because when I was at the Pendleton campus for over 15 years, I used to have to travel. Here's the double bridges right here. If I could draw on this thing. There's the double bridges, and if you're from Anderson, you know where the double bridges are. And if you're not, you call them the twin bridges. I've had somebody call them the twin bridges. No, they're not the twin bridges, they're the double bridges. And there's 24, and the old Huddle House is right here. And, oops, I'm sorry, the Huddle House is right here. It's closed now, so it's not there anymore. Pendleton High School is right here. And the Waffle House in Pendleton is right there. So, and there's Clipson Boulevard, or 76 right here. Sandy Springs is this way. Pendleton and Clemson is this way. Now, of course, why am I drawing this? Well, when I was at Pendleton, I traveled this road a good bit. If you have an 8 o'clock class at Pendleton and you get on Wild Hog Road at 20 minutes till or 7:40, even though it takes 16 minutes to travel 187, you're going to be late. Why are you going to be late? Well, there's something interesting. There's two things interesting about Highway 187. One, it's a straightaway pretty much. There's not a lot of curves. And two, it's hard to pass, okay, because there's so much traffic on it. Because there's a lot of people from Pendleton heading toward Anderson. There's a lot of people from Anderson heading toward Pendleton. So why will you not make it? Because usually when you get on the road right here at Garrett's, there's going to be a little blue-haired old lady get right in front of you. And y'all know the Little Blue-Haired Ladies Club. What do they do? What does the Little Blue-Haired Ladies Club do when they get in front of you? Come on, people. Y'all all had them in front of you. What do? That means I want y'all to answer the question.
Slow down.
They slow down. They go 33.5 miles an hour, no matter where they go. Say again?
Yeah, they go 33 and a 45.
Exactly. They go 33 miles an hour, no matter where they go. Now, you're going to get behind these two people, or these people, and they're going to stay on Highway 187, and you're going to get to Pendleton High School, and Pendleton High School is about a quarter of a mile from the red light there in Pendleton. And you're going to say to yourself, when you get about 200 feet from the red light, you're going to say, this person's going to turn left. And just as soon as you say that, what happens? Just right up here at this 187 sign, you get about 200 feet from the red light, and you're heading toward Pendleton. You're heading toward Pendleton, so you're going to turn on your left turn signal. And you say to yourself, that woman is going to go left. And what happens right after you say that to yourself? She turns on what? Her left turn signal. And wow, you have just predicted the future. True or false? Now, this is going to go a whole lot better if y'all interact with me, okay? Let's talk about this, all right? I'm going to show y'all something, and it's a pretty good, you know, pretty easy to do, okay? I'm going to show y'all something over here. Well, I can't bring it over there. Well, there's a button on your, looks like a little microphone. You can hit that button and you can talk. Did y'all know that?
Yes, sir.
Well, I appreciate you talking, Mr. Jermaine, but you're not the only one that's talking. The rest of the class needs to talk too. I don't know what their problem is, but they need to talk. All right, you have not predicted the future, okay? Why not? Because no one can predict the future. No one can predict the future. If you ever meet somebody that tells you they can predict the future in some certain way, what's the first thing you're going to ask that person?
I'm sorry, what was the question?
I said, if you ever meet somebody that tells you they can predict the future in some way, some form, what's the first question you're going to ask that person?
When am I going to die?
No.
Is it,
What is the most important thing to all of us? Money and time. What's the first thing you're going to ask that person? What are the lottery numbers going to be Friday afternoon?
Yep.
And they're going to say, oh, well, that's not what I do. I know you're a fraud. You can't tell the future. Shut up. Okay. That's not what I do. No, what I really do is I read you, and I read you really well, because if you're asking for the future, that means you're insecure about the present. So I can feed off of that, and I can ask you 20 questions, and I can figure out pretty much anything I want to figure out asking you 20 questions by law of deduction. Have you ever noticed that somebody that tells the future, quote, tells the future, they have to ask you questions? Have you ever noticed that?
Yeah, gather information.
Exactly. So they're a con artist. Now, what did you do? Now, this is in green because this is basically Hubert's definition of statistics. Placing a number from 0 to 1, that means a decimal, on a prediction based on, you could say statistics, but excuse me, you can say stats, math, data, whatever you want to call that, experience, or logic. Now, I didn't use mathematics or data on this one. I used experience and logic. What did I tell you I did for 15, 16 years? I traveled 187 because anybody that lives in West Anderson, West LA, where's West LA? Well, anywhere out here, okay? Anybody that lives, why didn't I say Townville? Well, Townville, you can hit 85 and you can travel and go 85 and hit Wild Hog Road on 85. So that's why I leave Townville out. Okay. West Anderson, if you don't travel, if you're going to Pendleton or Clemson or Sandy Springs, and you live in West Anderson, which is basically from 28 bypass to the double bridges, you're going to travel Wild Hog Road. Okay. Unless you'd like to go through all the red lights of 28 bypass, Liberty Highway / 28 bypass / Clemson Boulevard. Okay. Now, if you like that punishment, then you do, that's the way you go. But if you are living in West Anderson and you need to go to Pendleton, Clemson, or Sandy Springs, you're going to use Wild Hog Road. Okay. Now that's the experience, and me traveling it for 16 years, 15 or 16 years. I know that every time I get on Wild Hog Road, somewhere that first mile, which is both sides of I-85, somewhere in this vicinity right here, somewhere in that vicinity, I'm going to hit the Blue Haired Ladies Club. Okay, and they're going to get in front of me. All right. Now, the experience tells me that, but what about the logic? Well, what is at the end of Wild Hog Road? You're either going to go to Sandy Springs or you're going to go to Pendleton / Clemson. Why did I predict that she's going to Pendleton, and why would I get it right based on logic? Now, anybody from Pendleton or Sandy Springs or West Anderson can answer this question. Why do I know she's going to turn to Pendleton and not turn right to go to Sandy Springs?
Because she wouldn't have taken that road.
Exactly, because look at here. This road right here goes to Sandy Springs. This road right here goes to Sandy Springs. Actually, you could have took this road, but that'd been going Bass Acres, goes to Sandy Springs. And this road right here goes to Sandy Springs. So if she was going to Sandy Springs, she would have took a right at one of 4 places on the way through Wild Hog Road. So logic and experience tells me that if she's gone by Pendleton High School, there's probably a 95% chance that she's going to turn left. Now, what did I just use? Did I predict the future? No. What I just used is probability. Probability is assigning a number between 0 and 1, which means a decimal, on a prediction based on mathematics, experience, or logic. This is based on experience and logic. Now, when you meet somebody that says they can tell you the future, please don't fall for it. How many of you have played 20 questions before? Or 15 questions, or 10 questions, or 100 questions? How many of you have played a game where you asked at least 10 questions? So raise your hand. You can raise your hand. That's good. Y'all not going to talk to me, but raise your hand at least. Okay. Well, most of you have done that. That is called deduction. I'm thinking of a living being, okay? The first thing you're going to ask, is it an animal or is it a person? Okay? And I'll say it's an animal. And then you're going to say, does it have 2 legs or does it have 1 leg? Or 4 legs, I'm sorry. It has 4 legs. Does it eat meat or does it eat grass? Well, it can eat both, but it eats grass. And by the time you get to the 10th question, you know I'm thinking about a cow. Okay? Y'all just told the future. Y'all just read my mind. No, you just used mathematics. Deduction is part of mathematics and logic. So if anybody ever says to you that they can read your mind or they can tell your future, all you need to do is ask them one question. If they can't answer the lottery question, they're a fraud. Okay? Now, let's get to talking about probability. Probability is not very difficult. Let me get to my handy dandy. There we go. And go down here, Instructor Resources, and Resources. And I'm going to pull up. Where's my PowerPoints? I don't use PowerPoints very often, but every once in a while. And why is that thing way up there? And I can't get to it. Okay, 5.1. I just want to cover a few things that are on the slides. And let me close this out. There we go. All right, please let me know if you can see the slideshow. Can y'all see it?
Yes, sir.
Okay, thank you.
Yes, sir.
Appreciate it. All right, so what is probability? And there it is. Now, I'm not gonna, you don't have to write that down. Measure of the likelihood of a random phenomenon, chance of occurring. Probability describes the long-term proportion of which a certainty outcome will occur in situations with short-term uncertainty. Okay? Probability deals with experiments, blah, 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 outcomes. Okay, write this down, law of large numbers. I need you to write that down because that is a standardized test question, as well as it's very important that you understand the law of large numbers. So write that down. there was a couple of students at MIT, this is a while back, and they took a roll of quarters and they measured and weighed and scanned those quarters, and they put all that information into a computer and created an algorithmic quarter based on all of those quarters, measurements, balance, weights, heights, lengths, and all that good stuff. And they wrote a program how, and there's two types of probabilities. What do you mean, Hubert? Well, there's two types of probabilities. Hold on a second, I'm gonna try to get this to work. There's called the physical probability. Do y'all see me writing? I hope y'all do.
Yeah. Yes.
The physical probability is what somebody actually does. And the theoretical probability, if I spell it right, is based on the numbers. Let me give you an example. The theoretical probability of heads on a coin is 50%, 0.5. Because there's one side that's heads and there's two sides of a coin. So 1/2 is equal to 0.5. If you flip that coin 10 times and it comes up heads 4 times, then your physical probability is 4/10, which is 0.4. These two do not match. The law of large numbers states those two guys, they took that algorithmic program and they flipped that algorithmic coin in the computer a number of times to get that 0.4 to equal that 0.5. Does anybody have any idea how many flips it took for that physical probability to equal the theoretical probability? Does anybody want to take a guess?
1,000.
1,000. Got a guess of 1,000. Anybody else have a guess? It took, and write this down, it took 100,000 flips for the physical probability to come out to be 0.4999995. It took 100,000 flips to get the physical probability to equal the theoretical probability. Now, what does Hubert say the law of large numbers does? I say it's a good way to cover your backside. If you are in a position in the future where your paycheck depends on how well you do your research and how well you predict an outcome probability, then you better make sure you don't pull 4 samples, you better pull 4,000 samples. Okay? That's why we have the law of large numbers, whether you're dealing with statistics or you're dealing with probability, which they both go hand in hand. Because if I'm making a prediction, I'm using probability, and if I'm using it off of data, that's statistics. So if you are working for a company in the future and they want you to predict something, you better make sure you don't pull 4 samples. You better make sure you pull 400 or 4,000. Now later on in chapters 7 and 8, and 9 and 10, we're going to talk about how many do we pull. how do you come up with that number? We're going to talk about that, I think, in chapter 9, I think. Chapter 9, yeah, chapter 9. So that's the law of large numbers. And there's two types of probability, physical probability and the theoretical. Theoretical is based on the numbers. Somebody tell me the probability of pulling a king out of a deck of cards. That means I want y'all to answer.
Is it 4?
4 out of what?
52?
You must have a deck of cards with you right there, do you?
I don't.
Well, how did you answer that question?
I know that there's 52 cards in a deck, and
Exactly.
honestly, it was a guess at the
Okay,
king.
so which one did you use? Did you use the physical probability or theoretical?
Physical.
Really?
Or was
Did you
it?
have the cards with you?
Oh, no.
Okay, so which one? Theoretical.
Yep.
Theoretical is based on the numbers. He did not have a deck of cards in front of him. And if he didn't have a deck of cards in front of him, he's basing it off of theoretical numbers. So remember that. Now I see something in the chat. Make sure nobody's got a question. Okay. Okay, good, Miss Strickland, 4 out of 52. And she doesn't have any cards in front of her, so she used theoretical probability. Theoretical is based on the numbers that you know in your head. What is the probability of rolling a 6 on a die? That means I want you
1 out of 6.
1 out of 6. And of course, you don't have a die in front of you. You didn't roll it. So how did you know that? It was based on the numbers that you remember. There's 6 sides to a cube. So that's theoretical probability. Way to go, Yates. All right. So next. Make sure you understand what an experiment is. We've already talked about experiment, that when you are actually engaged in the observation. Sample space. Collection of possible outcomes. A good example of a sample space, somebody's wanting to have 2 kids. What is the sample space for 2 kids? Boy, boy, girl, 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 boy, and what? Boy, girl. That's the sample space. The sample space is 4. An event is any collection of outcomes from a probability experiment. So that would be an event. The event is 2 children. Write that down. The event, what? The probability of 2 children. A couple wants to have 2 children. That's the event. The sample space is what are the possible outcomes. There we go. They're doing it right there. There's the sample space. Boy, 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 girl, girl, boy, girl, girl. The event is having a boy and a girl. There's the event. Oh, I'm sorry. At least have 1 boy. Okay, so that would be boy, girl, boy, boy. I meant girl, boy. The only thing I would tell you to do there, well, you write that down. That could be a standardized test question. I don't think I would ask that. Identify the outcomes of the probability experiment. Consider the probability of experiment of having 2 children. Well, I've already told you there's the outcomes. Boy, 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 girl, girl, boy, girl, girl. Determine the sample space. Well, technically, A and B is the same thing. Okay, and then define have one boy. It doesn't say two, it says one boy. And that would be boy, girl, and girl, boy. That's the event. The probability of an event, that's what it looks like. Probability of an event, that's the way it's written, must be greater than 0 and less than 1. I told you from 0 to 1, we already wrote that down. So the probability has to be a decimal between 0 and 1. If you get a negative, it's impossible. If you have greater than 1, that's impossible. So any test question, and you will see a test question, that either is not equal to 1 or is negative or over 1, is to immediately throw it out. Okay? The sum of all the probabilities must equal 1. This is a test question right here. I think there's 2 test questions on my test that check on this. And I know that's a standardized test question. They must equal 1. All the probabilities added together must equal 1. A probability model lists the possible outcomes of a probability experiment and each outcome's probability. A probability model must satisfy rules 1 and 2. Okay, are all these between 0 and 1? Yes. Think of change between 0 money and $1. There's 12 cents, there's 15 cents, there's 12 cents, there's 23 cents, there's 23 cents, there's 15 cents. So there's no negatives and there's nothing above $1. Now add them up and they should equal 1. And they do. That is a test question. You'll be given a table and they'll either have decimals or fractions in that table. Each one of them has to be between 0 and 1. No negatives and nothing above 1. And then if you add them up, they should equal 1. So you might want to write that table down right there and this down right here. And right above it, no negatives and no probabilities greater than 1. This is what they're asking you to do in that project. So I'm just going to go ahead and tell you, if you're a candy person or a goldfish person, instead of getting the regular ones, get the ones that's got different colors, because you're going to be, or animal crackers, different shapes. You're going to be doing that in the project. Okay? Okay, this, first of all, probability does not use words like impossible, certainty, perfect. Why do they not use words like impossible, certainty, and perfect? Because they're too defined. A lot of times you see the word expected in probability. They don't like to be, but if an event is impossible, the probability is 0. An event is certain if the probability of 1. If I get a probability of 0, does that mean that no way, no how that event's going to happen? Think of birth control. No. If I get a probability of 1, does that mean that you're going to hit 21 on the table as soon as you put down $100? No. So these two words are used for the scale, but I can tell you in probability, words like this They don't like to use words like this. An unusual event has a low probability of occurring. Write those three things down because that is a standardized test question. Now, there is a question on the test and the standardized test that says, if you have a 0 probability, does that mean the event cannot happen? Yes, true or false? If you get a 0 on a probability, does that mean the event will never happen? No. They say that some birth control is like 98, 99%. Does that mean that you won't get pregnant? No. There is a question on the test about 0 being impossible, and it is false. You do not throw out everything because you get 0. Just like you don't bet your house on a probability of 1, because it could come up not being a winner. This is how you find probability. The number something actually happens over the number of trials of the experiment. If I flip a coin 10 times and I get 4 heads, then probability of heads is 4 over 10, which is equal to 0.4. This is usually the physical probability. The number of times something actually happens over the number of trials tried, or number of times something is tried. Flipping a coin, 4 times I get heads over 10 flips. That would be an example of this formula. Relative frequency is physical probability. Empirical, you see the words empirical, that means physical probability. Keyword, observed. So you might want to highlight that word observed. Okay, I've never heard of pass the pigs, but there it is. And these are basically whatever. Razorback, trotter, snouter, learning jowler, leaning jowler, whatever. And they rolled pigs 3,939 times. So that'd be 32 over that, 137 over that, 365 over that, 767 over that, 1294 over that, and 1344 over that. And then they're going to ask you a probability. What is the probability of trotter? That'd be 365 over 3939. Estimate the probability that a thrown pigs land on side with a dot. That would be 1294 over 13 whatever. Hold on. 1294 over 39 whatever. Would it be unusual to throw a leaning jowler with 32 over 3,900? Yes, it would be unusual. Use the result of the experiment to build a probability model for the way the pigs land. Well, I told you that. 1344 over 39, 1294 over 39, whatever, 767 over 39, and so on. Side with dot, that would be 1294 over 39. And leaning jowler would be 32 over 39, whatever. These are 3 good test questions. There's a probability model. B would be 0.329. Right there. Now that means if they throw the pig 1,000 times, and you need to move the decimal 3 places to the right, that 329 times it would land on side with a dot. This is what you're going to be doing with your project. You're not going to be doing with throwing the pigs. I don't know what the heck that is, but you're going to be using it with shapes and colored candies, cookies, whatever the case may be. Leaning jowler would be 0.008, which is unusual. Classical method is when you're using the mathematics. What is the probability of a card out of a deck of cards? What is the probability of rolling a 6 on a die? What is the probability of heads on a fair coin? And again, number of ways something can occur over the number of possible outcomes. Notice you don't see a word that says observe. It's not observed because you don't have a die in front of you. You don't have a deck of cards in front of you. You don't have a coin to flip. You're basing it off of the mathematics that goes with the object. 52 cards in a deck of cards. 6 sides to a die. 2 sides of a coin. So classical method is what I said, theoretical. Now, since test questions cannot ask you to bring a deck of cards into a test, most of your test questions are going to be classical, based on the number that goes with the object. Okay, here it is. See, you don't have a bag of M&Ms in front of you. So they give you an example of M&Ms. 9 brown, 6 yellow, 7 red, 4 orange, 2 blue, and 2 green. What is the probability that it's yellow? 2 out of the total. Well, the total is 9, 6 is 15, 7 and 4, that'd be 25, be 26, 30, so that would be 2 over 30, 2 over 30. Comment the likelihood of a candy being yellow versus blue. Yellow would be 6 over 30 versus 2 over 30. So 6 over 30, you're more likely to get a yellow candy than a blue if you just pick it out of the bag. This is all standardized test questions and test questions, so Write that one down as an example also. You don't have to write it word for word. Just say 9 brown candies, 6 yellow candies, 7 red, 4 orange, 2 blue, 2 green, and then write down those questions and answer them. And again, I'm not trying to insult anybody's intelligence. I'm trying to go through this in a summary type way, so that way you can actually go do the homework and then send me questions. That way I can go into them after you ask, because I don't want to go too fast, but I don't want to insult anybody's intelligence. I know a lot of high school students have had probability and statistics in high school, so that's why I'm kind of going over this, and hopefully y'all will send me questions in the homework. And there's what I just told you, 2 out of 30, 6 versus 2, and 6 is a more likely outcome. So you're 3 times as likely to get a yellow than a blue. Here's a 6-sided die, see? 100 times, approximate the probability of rolling a 4. Well, the probability of rolling a 4 is 1 out of 6. So multiply 1 over 6, that would be 0.16 repeating. So multiply that by 100, that would be 16% or 17%. And of course, repeat the exercise for 1,000, that would be 170 times you would get a 4. So 17 and 170. I'm looking to see if there's any. Subjective means that I want to get into subjective later. I think I'm going to stop right here. We're going to stop at subjective. That's okay with y'all. Yeah, we'll stop at subjective. All right, I need you to put in your notes that we're stopping at a subjective. I want to stop there, and I'm going to shut this down. And I'm going to shut off the recorder. I need you to take your hands down so that you put it back in alphabetical order, please. Please take your hands down, please. Miss Martin and Yates, please take your hands down. And I'm going to shut off the recording and take the roll.